Good evening, and welcome to the Sleepless Curiosity. I'm glad you're here tonight, wherever in the world you're settling in from. Here's the strange thought we're sitting with tonight. Nearly 2 kilograms of the moon are locked away in laboratories in Beijing, and they came from a place no human eye has ever directly seen. Not through binoculars, not through the finest telescope ever built. The far side of the moon has been hidden from us since before we had language for hiding, and when scientists finally opened that container, the soil inside didn't match anything 60 years of moon rocks had taught us to expect. One small favour before we drift into it. While you're settling in, hit subscribe if you're new here, leave a like. Comment and tell me where you're tuning in from tonight. It always amazes me how far these quiet little broadcasts travel. So get cozy and let's ask what China actually pulled out of the dark side of the moon. Now let's slowly ease into this. Part 1. The face we never see. Every single night of your life, when you have looked up and found the moon hanging there, pale and patient above the rooftops, you have been looking at the same face. Always the same face. Not because the moon holds still. It doesn't. It spins on its axis every single day, just like the Earth does. But it spins at exactly the same rate that it orbits us, locked in step, tidally bound to our planet in a slow gravitational dance that began billions of years ago and has never once broken stride. The result is that one hemisphere of the moon has been turned permanently toward Earth since long before there were eyes here to watch it, and the other hemisphere has been turned permanently away. You have never seen it. Your grandparents never saw it. No human being who ever lived before 1959, when a Soviet probe first swung a camera around the far edge and radioed back a blurry, grainy photograph, had any idea what was on the other side. Every myth about the man in the moon, every legend about the rabbit pounding rice, every ancient astronomer squinting up trying to read the patterns in that pale disk, all of it was built from half a story. The other half was simply gone, tucked around the curve of a world we could never walk behind. And here is the detail that should sit with you for a moment before we go any further. The two halves are not the same. Look up at a full moon on a clear night and you will see it immediately. That familiar patchwork of dark and light. Broad, smooth, grey-black plains spreading across roughly a third of the visible surface. These are the lunar seas, the Maria, ancient oceans of frozen lava that once poured out across the crust in the moon's early violent youth and then cooled into flat, dark stone. They are what give the moon its face. The eyes, the mouth, the shape people have projected onto it in every culture on Earth for as long as there have been people to look up. Turn the moon around and they are almost gone. The far side is a different world entirely. It is pale where the near side is dark. It is thick with craters where the near side is smooth. It has almost none of the great volcanic plains that define the hemisphere we know. Where the near side looks like it was flooded, the far side looks like it was simply left alone, battered by billions of years of impacts with nothing ever rising up from underneath to smooth the wounds over. Scientists call this asymmetry the lunar dichotomy, and it is one of the oldest open questions in planetary science. Two hemispheres of the same small world, shaped by the same sun orbiting the same planet, and yet built from what looked like two entirely different geological histories. For decades, nobody could say why. There were ideas, plenty of them, and most were reasonable on paper. Perhaps the great ocean of molten rock that covered the infant moon crystallized unevenly, cooling faster on one side than the other and leaving a thicker crust behind on the far side, one too thick for lava to ever push through again. Perhaps it was heat. The near side, facing Earth, may have absorbed more warmth from our planet during the moon's molten youth, keeping its interior liquid longer and letting volcanism run wild there while the far side quietly solidified. Perhaps it was a single catastrophic collision, some ancient impact so large it reorganized the entire structure of the young moon and left one hemisphere fundamentally different from the other from that day forward. Each of these ideas had its defenders. Each of them made predictions. And none of them could be tested, because testing them required something nobody had. Rock, actual physical material from the far side, sitting under a microscope, giving up its secrets to a mass spectrometer instead of to speculation. Think about what humanity had actually managed to bring home from the moon by the early 21st century. 6 Apollo missions. 3 Soviet robotic landers. Just under 382 kilograms of lunar material in total, collected across more than half a century of spaceflight, sitting in vaults and laboratories scattered around the world. Every gram of it, every single fragment, had come from the near side. Every textbook model of how the moon formed, cooled, and died had been built entirely from material collected on one face of a two-faced world. You cannot settle an argument about rock without rock. And for 50 years, that was exactly the argument nobody could settle. The far side was not just unphotographed for most of history. It was unsampled. It was, in the truest sense, unknown territory. Sitting less than 400,000 kilometers away, permanently facing outward into the dark, permanently turned away from every spacecraft that had ever tried to land there. And landing there is not a small technical footnote. It is, in many ways, the entire reason the far side stayed a mystery for as long as it did. A spacecraft on the near side can talk to Earth directly. Point an antenna at the sky, and Earth is simply there, hanging in a fixed position, always in the same patch of lunar sky, no matter where on the near side you happen to be standing. A spacecraft on the far side has no such luxury. The bulk of the moon itself, more than 3,000 kilometers of solid rock, sits directly between it and home. Radio waves do not bend around that kind of obstacle. They do not curve gently over the horizon the way light bends through Earth's atmosphere at sunset. They travel in a straight line and stop the moment something solid gets in the way. Which means that for most of the space age, landing something on the far side was not simply difficult. It was, for all practical purposes, impossible to operate once you got there. You could crash a probe into it, as the Soviets eventually did. You could photograph it from orbit. But landing something gently, keeping it alive, and then talking to it long enough to run an actual mission required a piece of infrastructure that did not exist yet. A relay, something sitting in exactly the right position in space to see both the far side of the moon and the Earth at the same time, catching signals from one and forwarding them to the other, acting as a kind of switchboard hanging in the dark between two worlds that could not otherwise speak to each other. Building that relay and then building a mission precise enough to use it would take decades. It would take a launch vehicle capable of reaching the moon reliably. It would take an autonomous landing system smart enough to navigate terrain nobody on Earth could see in real time. Because by the time a camera image reached mission control and a human decided what to do about it, the spacecraft would already be sitting in a crater it should have avoided. It would take a level of precision engineering that for most of the 20th century simply did not exist anywhere on the planet. So the far side waited. It sat there, pale and cratered and ancient, holding its answer to a question scientists had been asking since the first grainy Soviet photograph came back in 1959. What actually happened here? Why does this hemisphere look nothing like the one we know? And whatever the answer was, it was going to require someone to go and physically pick it up. That is where we are heading tonight. Not toward speculation, and not toward another decade of competing theories about crust thickness and ancient heat gradients. Toward an actual landing on an actual crater floor on the far side of the moon, and toward a scoop of soil that would turn out to be stranger than almost anyone expected. Because when that soil finally reached a laboratory bench on Earth, the first thing scientists measured about it was something as simple as how heavy it was for its size. And the number that came back was wrong. Part 2. The wound at the bottom of the world. To understand why anyone would choose to land in the specific spot they chose, you have to go back much further than the mission itself. You have to go back roughly 4.5 billion years to a moment so early in the moon's history that the solar system around it was still a shooting gallery of leftover debris, still full of asteroids and planetesimals slamming into every young world that had the misfortune of being in the way. Somewhere in the southern hemisphere of the lunar far side, something enormous hit the moon. We do not know exactly what it was. We do not know its precise mass, its precise speed, or the precise angle at which it struck. What we do know is written into the ground itself in a scar so large it is difficult to hold in your mind all at once. It is called the South Pole Aitken Basin, and it is the largest confirmed impact basin anywhere in the entire solar system. Not just on the moon, anywhere. It measures roughly 2,500 kilometers across, a wound so wide that if you stood at its center, the curvature of the moon itself would hide the rim from view in every direction. It is the deepest structure on the lunar surface, and based on crater counting and isotopic dating of nearby material, it formed somewhere between 4.2 and 4.3 billion years ago, in the earliest, rawest chapter of lunar history. Whatever struck the moon that day did not simply scratch the surface. Gravity measurements taken from orbiting spacecraft show that the crust beneath parts of the basin is among the thinnest found anywhere on the moon, thinner than it has any right to be if the impact had merely gouged out a shallow crater. Modelling of the impact suggests it excavated material from somewhere between 80 and 120 kilometers below the original surface, reaching straight through the lower crust and quite possibly punching into the mantle itself. That is not a crater in the way you might picture one. That is a hole torn down into the deep interior of a world, a place where material that had never been anywhere near sunlight was suddenly thrown up and scattered across the surface. And nested inside that colossal scar sits a smaller one. The Apollo Basin, a peak ring structure roughly 490 kilometers wide, itself one of the deepest and largest impact features on the moon, sitting like a scar inside a scar. One catastrophe layered on top of an older, larger catastrophe. And inside that basin, on a flat plain of dark, ancient basalt lying between the inner ring of mountains and the southern rim of the crater, is where a Chinese spacecraft named Chang'e 6 came to rest. Roughly 1.5 degrees south, 154 degrees west. A landing site chosen with a very specific hope in mind. If the ancient impact that carved South Pole Aitken really had reached down into the deep mantle, then somewhere in that basin, mixed in with the ordinary surface soil, there might still be fragments of that deep material lying around, waiting to be picked up. Scoop the ground here, and you might, almost by accident, be scooping up a piece of the inside of the moon. The terrain around the chosen landing spot was not gentle. Wrinkle ridges wrinkled across the plain, like folds in old fabric. Scattered among them were kipukas, islands of older, higher ground that ancient lava flows had simply flowed around rather than over, leaving little raised patches of pre-existing terrain poking up through the younger basalt like stepping stones. The lander itself came down on the flat edge of a small impact crater, about 50 meters wide and 3 meters deep. Its basalt floor dated from crater statistics to somewhere between 2.79 and 2.87 billion years old. Old enough to have witnessed most of lunar history unfold, young enough to still hold on to a coherent story. The mission itself launched on the 3rd of May 2024 at 27 minutes past 11 in the morning, Coordinated Universal Time, riding a Long March 5 rocket up from the Wenchang launch site on Hainan Island. It was the 6th robotic lunar mission flown by the China National Space Administration, following a naming tradition that stretched back to the very first mission in the program, each spacecraft named after the goddess of the moon in Chinese mythology. The full stack weighed roughly 8,200 kilograms at launch. The lander itself accounted for about 3,200 of that. A small ascent vehicle, tucked on top, designed to eventually carry the collected samples back off the surface, weighed around 700 kilograms on its own. 5 days after launch, the spacecraft slipped into a 12-hour orbit around the moon, and here is where the first real technical hurdle of the entire mission had to be solved. Because you cannot simply talk to a spacecraft sitting on the far side of the moon. Radio waves do not bend around 3,500 kilometers of solid rock. Every command sent from Earth, every fragment of telemetry sent back, every photograph, every measurement had to be relayed through something else first. That something else was a satellite called Chang'e, already stationed at a carefully chosen gravitational balance point where it could see both the far side of the moon and the Earth simultaneously, acting as a switchboard hanging in space between two worlds that could not otherwise speak to each other. Without it, Chang'e 6 would have touched down on the far side and simply gone silent, deaf and mute the moment it crossed the lunar horizon, cut off from Earth as completely as if it had never launched at all. On the 30th of May, the lander and ascender separated from the orbiter that had carried them to the moon. 2 days later, from an altitude of 200 kilometers, the descent began. This is the part of the mission that had no room for human intervention, because there was no time for it and no signal path to carry it, even if there had been. The spacecraft came down using an autonomous obstacle avoidance system, reading the terrain beneath it in real time through a visible light camera and a laser 3-dimensional scanner, picking out boulders and slopes as it fell, steering itself around hazards that no one on Earth would even know existed until long after the landing was already decided one way or another. 17 minutes after the descent began, it was down, sitting on the floor of that small crater in the Apollo basin, the first spacecraft in human history to make a soft, controlled landing on the far side of the moon. Then the collecting began. A robotic scoop worked the surface. A drill reached down roughly 2 meters beneath it, pulling up a core sample that preserved the layering of the soil the way tree rings preserve the seasons. The surface scooping was carried out in 8 separate passes, each one no deeper than 3 centimeters, gradually building up a total of around 1,610 grams from surface material alone. And in one small, almost accidental detail that would go on to circulate across Chinese social media within days, when the drill withdrew from the ground, the hole it left behind happened to trace the shape of the character for Zhong, the first character in the Chinese name for China. Nobody planned it. Nobody could have planned it. It was simply the shape a drill leaves in soft lunar soil when it is pulled straight back out of a narrow hole, and it happened to look, for anyone glancing at the image, uncannily deliberate. There was one more passenger riding along on the lander, a small rover weighing about 5 kilograms, wrapped in gold insulating film that earned it an affectionate nickname translating roughly to Golden Toad. It carried its own tiny solar panels and an infrared spectrometer for studying the composition of the surface and hunting for signs of water ice in the soil. But its most charming task was simpler than any of that. After the main sampling work was finished, the little rover detached itself, drove a short distance across the crater floor, chose an angle, and photographed the lander sitting there alone on the far side of the moon. It did the entire thing on its own, with no one steering it in real time, because there was, once again, no way to steer it in real time. Every decision that little machine made, it made for itself, 400,000 kilometers from the nearest human being, on a hemisphere of the moon that no human eye had ever directly seen. At 38 minutes past 11 at night on the 3rd of June, the ascent vehicle ignited its engine and lifted off the top of the lander, carrying the collected samples upward into lunar orbit. It was the first time in the history of spaceflight that anything had ever lifted off from the far side of the moon carrying cargo bound for Earth. 3 days later, at 48 minutes past 6 in the morning, the ascender found the orbiter waiting in lunar orbit and docked with it automatically, entirely robotically, with no human pilot flying either vehicle. 36 minutes after that, the sample container was transferred across into the return capsule that would eventually carry it home. Then, for a while, the mission went quiet. Part 3. The Long Fall Home. On the 21st of June, the service module appears to have fired its engines to break free of lunar orbit and begin the journey back toward Earth. There was no live announcement at the time, no dramatic countdown broadcast to the world. What we have instead, oddly, is a scattering of reports from amateur optical and radio observers scattered across the globe. Hobbyists and enthusiasts who happen to be watching the right patch of sky at the right moment and noticed something that looked very much like an engine burn, a faint change in brightness and trajectory that matched exactly what you would expect from a spacecraft leaving lunar orbit. Sometimes the most significant moments of a space mission are witnessed not by mission control, but by a handful of amateurs with telescopes in their backyards, quietly piecing together a puzzle that the professionals are simply too busy managing in real time to narrate. 4 days later, a re-entry module weighing around 300 kilograms separated from the rest of the spacecraft and struck the top of Earth's atmosphere over the Atlantic Ocean. It did not come straight down in a single steep plunge the way you might picture a returning spacecraft. It skipped, bouncing off the upper atmosphere once, shedding speed the way a flat stone skips off the surface of a lake before finally losing enough momentum to commit to the final descent. It is a technique called a skip re-entry, and it exists precisely because a capsule returning from the moon comes in far faster and far hotter than one returning from low Earth orbit, fast enough that a single direct plunge would subject it to heat and deceleration forces that push the very edge of what any heat shield can survive. Skipping once lets the capsule bleed off speed gradually, a controlled compromise between the physics of atmospheric friction and the fragile cargo sealed inside. At 7 minutes past 6 in the morning on the 25th of June, a parachute opened over Siziwang Banner in Inner Mongolia, the same recovery zone China has used for its crewed and robotic return capsules for years. Helicopters reached the capsule within minutes, lifting it away from the grasslands where it had come to rest, 53 days after launch, carrying inside it something that had never before existed anywhere on Earth, a physical sample of the lunar far side. And now, finally, the actual scientific work could begin. 3 days later, in Beijing, there was a formal ceremony. Chang'e, head of the China National Space Administration, handed the sealed sample container over to Ding Chibiao, vice president of the Chinese Academy of Sciences. Certificates were exchanged, photographs were taken. It had the feeling of any national milestone ceremony, formal handshakes and careful language. But at the press conference that followed, the mission spokesperson, Ge Ping, said something that is easy to skip past if you are not listening closely. He said the samples appeared more viscous than previous lunar samples, that there were clumps. He was careful about how he phrased it, calling these observable characteristics rather than conclusions. A man describing what he could see with his own eyes, and very deliberately declining to say what any of it meant. He was, without quite realizing it yet, describing the very first discovery of the mission. It simply did not look like one at the time. It looked like a passing observation at a press conference, a small aside about texture. It would turn out to be the first hint of something genuinely strange sitting inside that container. The first real measurement anyone took, once the samples reached a proper laboratory, was density. And it came back wrong. Here is what wrong means in this context. Lunar soil, based on everything collected from the near side across more than half a century of sample return missions, sits within a fairly well understood range. Chang'e 5 soil, brought back from the near side in 2020, had a bulk density of about 1.24 grams per cubic centimetre. The Apollo samples, collected across 6 different landing sites decades earlier, ranged anywhere from about 0.75 up to 2.29, a fairly wide spread depending on exactly where on the near side you happen to be scooping. The Chang'e 6 soil measured 0.983 grams per cubic centimetre. Let that sit with you for a moment. That is barely denser than water. It is the first material ever collected from the far side of the moon, and it is fluffier, lighter, more porous than any lunar soil humanity had ever handled before. Not slightly lighter, measurably, consistently lighter, both in the bulk density of the loose soil as a whole and in the true density of the individual grains that made it up. And remember, this measurement was taken here on Earth, under Earth's full gravity, after the sample had been shaken through a launch, a lunar ascent, a docking maneuver, an interplanetary transfer, a skip re-entry, and a parachute landing. In its natural resting state on the lunar surface itself, under 1/6 of Earth's gravity, that soil would have been looser still, an almost impossibly delicate structure of tiny grains barely touching one another. So the obvious question, the one every geochemist in the room was already asking before the density measurement had even finished printing out, was simply this. Why the answer, it turned out, was about ingredients. Lower density means lighter components, and when researchers ran a full mineral analysis on the sample, breaking it down grain by grain to identify exactly what it was made of, the ingredient list did not look anything like the near side. The soil was roughly 31.5% plagioclase, a pale, low-density feldspar mineral, nearly 20% augite, 10% pigeonite, around 3.5% orthopyroxene, just under 30% amorphous glass, tiny beads and fragments formed by the intense heat of ancient impacts, cooling too fast to form proper crystal structure. And olivine, a dense, heavy mineral common in many types of volcanic rock, came in at just half of 1%. For comparison, Chang'e 5 soil from the near side had run about 4.3% olivine and about 20.7% glass. The far side sample had roughly a tenth of the olivine and considerably more glass. But the detail that mattered most, the one that would end up driving the entire scientific investigation forward, was the orthopyroxene. That particular mineral is not typical of the local basalt at the Chang'e 6 landing site. Its presence there means something. It means material arrived at that spot from somewhere else, carried in by forces that had nothing to do with the slow local cooling of lava on the crater floor. And that was the second major finding buried in the soil. This sample was not purely local. Based on the proportion of orthopyroxene relative to the total pyroxene content of the sample, researchers estimated that at least 11% of the material scooped up at the landing site was foreign, debris flung in from somewhere else on the moon entirely. Factor in the excess plagioclase alongside it, and that foreign fraction could be even higher than that. Separate analysis of the bright ejector rays crossing the dark plane around the landing site, streaks of lighter material visible from orbit radiating outward from distant, younger craters, independently suggested contamination of at least 13%, which means the sealed container sitting in that laboratory in Beijing did not simply hold a scoop of local ground, it held a mixture. Local basalt, mixed with wreckage thrown in from other impacts scattered across the far side, some of them potentially reaching very deep indeed into the ancient interior of the moon. The grains themselves, once examined under magnification, turned out to be almost unimaginably fine. Researchers measured more than 72 million individual particles smaller than a single millimeter across. 95% of them fell between roughly 1 and 11 micrometers, averaging about 5.5 micrometers overall. In geological terms, that places the material somewhere between clay and fine silt. In practical, everyday terms, it is dust, the slow accumulated product of billions of years of micrometeorite bombardment, grinding solid rock down into powder in the airless vacuum of the lunar surface, a process with no wind and no water to ever smooth it, round it, or wash it away. Among that fine dust sat larger fragments, and those fragments told their own story. Basalt made up 30 to 40% of the coarser material. Breccia, broken rock that had been shattered by ancient impacts and then welded back together under the heat and pressure of later collisions, accounted for another 30 to 40%. Agglutinates, small grains of soil fused together by impact glass, made up 20 to 30%, and about 10% were pale fragments dominated by anorthosite and norite, rock types associated with the moon's earliest, deepest crust. There were glass beads too, scattered throughout the sample, small and rounded, coloured black, brownish yellow, white and green, each colour a signature of the specific temperature and chemistry of whatever ancient impact had melted and flash cooled it into existence. Chemically, the local basalt at the landing site turned out to be low in titanium, low in aluminum, and low in potassium. The soil showed very little uranium and thorium, far below the concentrations found in the potassium-rich terrain that dominates much of the near side. The same radioactive element-rich terrain that helped keep near-side volcanism running for so much longer than anywhere else on the moon. Whatever this place was, it had clearly not been built from the same enriched material that produced the great dark seas visible from Earth on any clear night. So by this point, the team had ground truth. They knew, in fine detail, exactly what the far side landing site was made of. What they did not yet know, what nobody yet knew, was what had happened to it, why the mineralogy looked the way it did, why the isotopes, when they finally got around to measuring them properly, would come back carrying a signature nobody had ever seen in lunar rock before. That question would fall to a research team working under Professor Tian Hengqi at the Institute of Geology and Geophysics of the Chinese Academy of Sciences, and their reasoning would begin with something deceptively small. A single element. Potassium. Part 4. The thermometer that remembers the worst day. To understand what happened next, you need to understand a strange and elegant fact about a very ordinary element, one that sits in your bloodstream right now, one that is in the banana you might have eaten this week, one that geochemists call a moderately volatile element. Potassium does not need to be blasted apart to leave a rock behind. It does not need violence in the way some elements do. It only needs heat, enough heat, and it simply evaporates, drifting away as vapor the same way water leaves a puddle on a hot day, except at temperatures that would vaporize stone. And here is the detail that makes potassium so useful to a geochemist, the detail that turns an ordinary element into something closer to a fingerprint. Potassium does not exist in nature as a single uniform substance. It comes in more than one isotope, more than one version of itself, each one chemically identical but physically slightly different in mass. Potassium-39 is the lighter, more common version. Potassium-41 is heavier, rarer, and just a little more sluggish. When molten rock boils away into a vacuum, the two isotopes do not leave at the same rate. The lighter isotope, potassium-39, escapes more readily. It is quicker, easier to knock loose, easier to fling off into space. The heavier isotope lags behind, held slightly more firmly by its own extra mass. So what remains behind, what stays trapped inside the cooling rock once the boiling stops, becomes progressively enriched in the heavier version, left slightly heavier in its isotopic makeup than it started out, which means the potassium sitting inside any given piece of rock is not simply a chemical ingredient. It is a thermometer. Not a thermometer of today, not a record of the rock's current quiet temperature sitting in a laboratory drawer. A thermometer of the worst day that rock ever had. Measure that isotopy ratio precisely enough, and you are reading a record of temperature, of pressure, of an entire violent history left behind by an event that may have happened billions of years before there was anything alive anywhere in the solar system to witness it. This is the tool Professor Tian's team decided to turn on the Chang'e 6 basalt fragments, and almost immediately they hit a wall. The Chang'e 6 samples were, as we've already established, mostly dust. Fine, powdery, difficult to work with. Finding individual solid grains large enough to run a proper isotope analysis on was genuinely difficult, and precision potassium measurement had, up to that point, traditionally required far more material than the team actually had available to them. Tian later described this, in interviews after the study was published, as the major technical challenge of the entire project. Not the physics, not the modelling, simply having enough rock to work with. So rather than requesting a larger sample allocation, which was not really an option given how precious and limited the entire return cargo was, the team rebuilt the method itself from the ground up. They developed what they called an ultra-low consumption potassium isotope protocol, a laboratory technique capable of achieving high precision measurement using only a few milligrams of material, a fraction of what had previously been considered the minimum workable amount for this kind of analysis. In the end, they worked with 4 basalt fragments. The heaviest weighed about 19 milligrams, the lightest about 14. 4 small stones, sorted out of the loose soil under a binocular microscope in a clean laboratory, 1 grain at a time, washed carefully in ethanol to strip away any clinging surface dust that might contaminate the reading, and scanned with X-ray tomography to confirm what they appeared to be internally, without ever having to cut them open and risk losing material in the process. Then, finally, they were dissolved, chemically purified, and fed into a mass spectrometer. And the result did not match anything from the near side. The Chang'e 6 basalts came back isotopically heavier in potassium than every previously documented lunar basalt ever measured. Heavier than the Apollo samples. Heavier than Chang'e 5. Heavier than the small collection of lunar meteorites that have occasionally been found scattered across Earth's deserts and ice sheets, blasted off the moon by ancient impacts and eventually falling to Earth on their own, entirely independent of any spacecraft. The offset averaged about 16/100ths of a part per thousand above the Apollo baseline, a difference so small it sounds almost trivial when you say it out loud, and yet in the world of precision isotope geochemistry, a difference that small is treated with the utmost seriousness. The iron isotopes in the same fragments came out heavier too, following the same unmistakable pattern. Now in isotope geochemistry, differences this small are never casually accepted. They are attacked methodically from every angle the team could think of, because the entire discipline runs on the principle that an extraordinary interpretation demands that every boring explanation be ruled out first, one by one, with actual evidence rather than assumption. So the team went hunting. Could it be cosmic rays? Over hundreds of millions of years, high-energy radiation striking the exposed lunar surface can trigger nuclear reactions inside rock, subtly altering isotope ratios through a process called cosmogenic production. It is a real effect, well documented in other lunar samples. So the team calculated the maximum possible contribution this process could have made, even assuming an unusually long exposure age of a full billion years, an upper limit far beyond what most lunar samples actually experience before being buried or reworked. The calculated effect landed comfortably inside their own margin of measurement error. It could not explain what they were seeing. Could it be contamination from the surrounding soil? Fine lunar dust, exposed directly to the harsh environment of the lunar surface for eons, does acquire heavy isotope signatures of its own through a process called space weathering. The slow bombardment of solar wind particles and micrometeorites that gradually alters the outermost layer of every exposed grain. But the 4 fragments the team had selected had been ultrasonically cleaned before analysis, and the X-ray tomography scans taken beforehand showed no impact breccia, no melt glass, no surface contamination lurking inside them. They were clean, solid basalt through and through. Could it simply be ordinary magma chemistry? Here the answer split cleanly in 2. Modelling the processes of partial melting, where rock deep in the mantle partially liquefies and rises toward the surface, and fractional crystallization, where different minerals solidify out of that magma at different temperatures as it cools, showed that these processes together could largely account for the heavy iron signature the team had measured. Iron behaves in a way, chemically, that made this explanation plausible. But potassium behaved differently. Because of the specific way potassium moves, or rather fails to move, during melting and crystallization. These ordinary magmatic processes leave its isotope ratio almost entirely untouched. Whatever had shifted the potassium in these rocks, it was not the normal everyday chemistry of magma rising and cooling. The magma itself could not have done it. Could it be the original impactor, then, the object that struck the moon and carved out South Pole Aitken in the first place, somehow mixed directly into the mantle and altering its chemistry from the outside in? The team ran the numbers for several plausible impactor compositions. Chondrites, a common and primitive type of meteorite, would have driven the isotopes lighter, not heavier, the opposite direction from what was actually measured, and would have left behind a distinct nickel signature that simply is not present in the samples. Iron meteorites contain almost no potassium at all, making them essentially incapable of shifting a potassium isotope ratio in either direction. And a body more like the large asteroid Vesta, with its own distinct chemical fingerprint, would have required an implausibly large fraction, at least 7%, of its own material to survive intact within the lunar mantle, while simultaneously pushing the iron isotopes in exactly the wrong direction to match what was observed. One by one, every ordinary explanation the team could construct failed to fit the evidence, which left the extraordinary one. Here, laid out plainly, is what the data actually seems to suggest. The mantle beneath the South Pole Aitken Basin does not merely contain heavy potassium today, sitting there as some inherited quirk of formation. It appears to have already been heavy before these particular basalts ever formed, before the lava that would eventually cool into the rocks Chang'e 6 collected ever rose up from below and solidified on the surface. The signature was not created on the way up. It was inherited from below, already present, already baked in. Something reached down into the deep interior of the moon billions of years ago and cooked it. Numerical simulations of the original South Pole Aitken impact, the one that carved out the largest confirmed crater in the entire solar system, suggest that the collision could have briefly raised local mantle temperatures to somewhere around 2,800 Kelvin. That is comfortably hot enough to vaporize potassium outright, turning solid mineral directly into gas. And the moon, unlike Earth, has no atmosphere to hold that vapor in place, no blanket of air to trap it and let it eventually settle back down. On an airless world, anything that boils simply leaves, escaping outward into space, carrying the lighter isotopes away with it and leaving the heavier ones behind, exactly the pattern the team had measured in those 4 small fragments. And the truly remarkable part, the detail that makes this whole story land with real weight, is how little material actually needed to escape in order to leave a mark this clear, still legible 4.5 billion years later. Part 5. 2% of nothing. And everything it changed. Under vacuum conditions, isotope separation turns out to be brutally, almost unsettlingly efficient. When Professor Tian's team modelled the process as a simple case of distillation, the same basic physics that governs a still separating alcohol from water, they found that a loss of just 2% of the total potassium in that region of mantle was enough, entirely on its own, to fully account for the isotopic signature measured in those 4 fragments. For iron, the figure was even smaller. Less than 2%. Sit with that number for a moment before we move on, because it is easy to let it slide past as just another statistic in a long chain of statistics. 2%. Not half the mantle boiling away, not some cataclysmic evaporation event stripping a hemisphere bare. 2% of one element, quietly lost to space in the searing aftermath of a single ancient impact. And that alone was enough to leave a fingerprint that a mass spectrometer on Earth could still read, clearly and unambiguously, 4.5 billion years later. It is the geochemical equivalent of a single afternoon leaving a scar on a person's memory that outlives every other day of their life. Almost nothing happened by the standards of planetary catastrophe, and it left a mark that has not faded since before there was a sun old enough to have made most of the elements in your own body. The paper reporting this discovery was published in the Proceedings of the National Academy of Sciences on the 12th of January. In careful, measured scientific language, it laid out what the team believed they were the first to demonstrate directly: that an impact of sufficient scale can do more than excavate a planetary body, more than melt it, more than simply rearrange its geology through brute mechanical force. It can boil it. It can reach down into the deep interior of a moon or a planet and drive volatile elements straight out of solid rock and off into space, leaving behind a permanent isotopic scar on material that would go on, tens of millions of years later, to rise back up as fresh lava and cool into the very basalt scooped up by a robotic arm on the floor of a crater within the largest impact basin in the solar system. And this finding carries a consequence that reaches far beyond the boundaries of that one ancient collision. Volatile elements are not just chemical trivia sitting quietly in a rock's composition. They are part of what makes magma in the most literal and practical sense. They lower the melting point of mantle material. They help molten rock rise more easily toward the surface, working almost like a lubricant in the deep plumbing of a planet's interior. Strip volatile elements out of a region of mantle, and that region becomes measurably harder to melt, less willing to produce the kind of fluid, far-travelling lava that built the great dark seas on the moon's near side. Which means the dark seas themselves, the broad, smooth plains you have looked up at your entire life. The patches every culture on Earth has drawn a face or a rabbit or a woman carrying water into, their conspicuous absence on the far side may not be a simple accident of geography at all. It may be scar tissue. The lingering billion-year aftermath of a single catastrophic morning 4.5 billion years ago, when something massive struck the far side of a young, barely cooled moon and, in doing so, quietly turned down the volcanic potential of an entire hemisphere before that hemisphere had even finished forming. The research team is careful, appropriately careful, not to overstate their case. Their own published wording is that the impact contributed at least partially to the observed asymmetry between the two hemispheres. Not that it single-handedly explains the entire dichotomy on its own. The measurements, while striking, are preliminary, drawn from just 4 small fragments out of nearly 2 kilograms of returned material. The team has stated plainly that they intend to test the conclusion further, measuring other volatile elements to see whether the same pattern holds, and combining their geochemical results with numerical modelling to assess just how far the thermal effects of that ancient impact actually reached, whether they were confined to the immediate vicinity of the basin or whether their influence spread more broadly across the far side as a whole. But the shape of the answer is now visible in a way it never was before this mission flew, and it lines up with something else the same samples revealed almost as a side note. Analysis of the Chang'e 6 material suggests that the mantle beneath this hemisphere appears to hold measurably less water than the mantle beneath the near side. Less water, less potassium, less of almost everything that helps rock melt and rise and erupt onto the surface as fresh volcanic plains. Every strand of evidence pulled from that small, precious handful of dust and stone seems to be pointing, quietly and independently, toward the same underlying story. Whatever happened here billions of years ago did not just leave a crater. it left the entire hemisphere chemically diminished, less able to build the kind of dark, fluid seas that define the face we have spent our whole lives looking up at. Almost 2 kilograms of far-side material are now sitting in laboratories in Beijing, and the overwhelming majority of it has not even been touched yet. This is one study, examining 4 fragments out of a return that carried back roughly 130 times that much material in total. Separate research teams have already begun the painstaking work of tracing where each portion of the sample actually came from, reconstructing the complicated history of impacts and ejecta that mixed together to form the soil at the landing site. One such catalogue effort identified 1,674 major source craters scattered across the region, each one a candidate for having thrown debris onto the Chang'e 6 landing site at some point over the last several billion years, some of them drawing material from as deep as 3 kilometers below the surface. Together, those countless individual impacts appear to have delivered a mixed layer of foreign material roughly half a meter thick across the entire sampling region, a slow, patient accumulation of debris arriving from dozens of separate ancient collisions, all of it eventually settling into the same patch of ground that a robotic scoop would one day disturb. Their working estimate is that the returned material breaks down roughly like this. About 93% is ordinary local basalt, the ground truth of the landing site itself. About 6% is material specifically traceable back to the South Pole Aitken Basin, the fraction most likely of everything in that container to actually contain genuine deep mantle components carried up and out by the original impact, and roughly 0.5% is highland material arriving from entirely outside the basin altogether, flung in from some more distant collision elsewhere on the far side. 6%. That is the piece everyone studying this sample is really after. Somewhere in that container, mixed in among the fine grey dust, the tiny coloured glass beads, and the welded fragments of ancient breccia, there may be a handful of grains that genuinely are, in the most literal sense available to modern science, the inside of the moon. The rest of the work is still very much ahead. The orbiter that ferried the return capsule most of the way home never actually returned to Earth itself after releasing its precious cargo. Having done its job, it flew onward instead, and was eventually captured at a gravitational balance point in space beyond our planet, a stable pocket where the pull of the Sun and Earth roughly cancel out, and where it remains today, quietly parked, its main mission complete. In September of 2025, the Chang'e 6 mission team received the World Space Award from the International Astronautical Federation, formal recognition of what had been, by any measure, an extraordinary engineering and scientific achievement. Applications to study portions of the returned samples have opened to research institutions across China, and the China National Space Administration has publicly stated that it welcomes proposals from scientists in other countries as well, an invitation for the wider global research community to take part in unpacking what this small handful of far-side dust actually has to say. And more missions are already being planned for this exact region of the moon. Several space agencies around the world, working independently of one another, have their attention fixed squarely on the South Pole Aitken Basin, drawn there not only by the deep mantle material it may still be hiding, but by the permanently shadowed craters clustered near the lunar South Pole. Craters where sunlight has never once reached the floor in billions of years, and where water ice is believed to be locked away in the permanent cold, waiting for the right mission to come and confirm it directly. But step back from all of that for a moment. away from the crater catalogues and the isotope ratios and the mission timelines, and sit instead with the larger shape of the story. For the entire recorded history of our species, we have looked up at the same face. Every myth ever told about the moon, every careful naked-eye observation made by ancient astronomers lying on their backs in fields thousands of years before telescopes existed, every photograph taken through every instrument ever pointed skyward. And every one of the 11 successful sample return missions that came before this one, all of it was directed at a single hemisphere of a world that turned out all along to have two. We assumed, reasonably, that we understood the moon. What we actually understood was the side that happens to face us. And when we finally reached around, landed on the other hemisphere, and took a careful handful of its soil, what came back was soil too light to be familiar, glass scattered where geologists half expected solid stone, olivine that had nearly vanished from the mineral record entirely, and 4 small fragments, each one barely the weight of a raindrop, quietly carrying the chemical memory of a single ancient day when the deep interior of the moon grew hot enough, however briefly, to boil. Part 6. What the far side had already told us, quietly, from orbit. Before we go further into what the samples themselves revealed, it is worth pausing to understand something important. Chang'e 6 was not humanity's first encounter with the strangeness of the lunar far side. It was simply the first time we managed to touch it, to bring a piece of it home and put it under a microscope. For decades before that, orbiting spacecraft had been quietly gathering indirect evidence that something was fundamentally different about that hemisphere, and each new piece of evidence only deepened the puzzle rather than resolving it. The first hints came from gravity. In the early 1990s, and then more precisely in the following decades, spacecraft orbiting the moon began mapping tiny variations in the strength of lunar gravity as they passed overhead, variations caused by differences in the density and thickness of the crust and mantle beneath them. Denser material pulls a passing spacecraft slightly harder. Thinner crust, sitting closer to the denser mantle below, does the same thing. By tracking these minute gravitational tugs with extraordinary precision, scientists were able to build a rough map of what lay beneath the visible surface, without ever having to land or dig. What that map showed was startling in its clarity. The near side, especially beneath the Great Dark Maria, showed regions of unusually thin crust paired with dense, buried structures that planetary scientists came to call mass concentrations, or mascons, dense plugs of material, likely the cooled remnants of ancient impact basins that had been flooded and refilled with dense volcanic rock. The far side showed almost none of this. Its crust, on average, appeared to be significantly thicker than the crust on the near side, in some places by tens of kilometers. It was as if the moon had grown a heavier coat on one side of its body and a thinner one on the other, an asymmetry baked directly into its structural bones. Then came the missions dedicated specifically to gravity itself. In 2011 and 2012, a pair of twin spacecraft flew in tandem orbits around the moon, measuring the tiny changes in the distance between them caused by variations in lunar gravity as they passed over different terrain. The same basic technique used to map Earth's own gravity field from orbit. Their data refined the picture even further, confirming not only the crustal thickness difference, but revealing the internal structure of major impact basins in unprecedented detail, including the South Pole Aitken Basin itself, whose true scale and depth only became fully apparent through this kind of painstaking orbital measurement. At the same time, Other orbiting instruments were mapping the surface composition of the Moon using a completely different method entirely, reading not gravity, but light. Certain minerals absorb and reflect specific wavelengths of sunlight in distinctive, identifiable patterns, and by analyzing the reflected light from the lunar surface across a wide range of wavelengths, spacecraft could effectively fingerprint the mineral composition of the ground below without ever touching it. These surveys confirmed, from orbit long before Chang'e 6 ever launched, that the far side surface was dominated by different minerals than the near side, richer in the pale, ancient rock associated with the earliest lunar crust, and comparatively poor in the darker, iron-rich basalts that define the near side Maria. There was also the matter of radioactive heat. Certain elements, potassium, thorium, and uranium among them, are naturally radioactive, slowly decaying over billions of years and releasing heat as they do. Orbiting gamma-ray spectrometers, capable of detecting the faint gamma radiation given off by these decaying elements, mapped their distribution across the entire lunar surface, and the resulting maps showed something remarkable. A large portion of the near side, an area sometimes informally called the Procellarum Creep Terran, using an acronym built from the chemical symbols for potassium, rare earth elements, and phosphorus, showed a dramatic concentration of these heat-producing elements, far higher than almost anywhere else on the Moon. The far side, by contrast, showed almost none of it. This was for a long time one of the leading explanations for why the near side had so much volcanic activity and the far side had so little. If the near side crust and upper mantle were unusually enriched in radioactive elements, then that region would have generated more internal heat over billions of years, kept its interior warmer for longer, and remained capable of producing molten rock and volcanic eruptions long after the far side's cooler, less radioactive interior had effectively shut down. It was, and still is, a genuinely compelling piece of the puzzle. But it left an obvious question unanswered. Why was that heat-producing material concentrated so heavily on one side of the Moon in the first place? Why did the near side end up enriched and the far side end up depleted if both hemispheres supposedly formed from the same collapsing cloud of material, cooling under the same physical laws? Some researchers proposed that it traced back to the very earliest chapter of lunar history, to the enormous magma ocean that is thought to have covered the entire young Moon shortly after its formation, a global sea of molten rock hundreds of kilometers deep, slowly cooling and crystallizing over tens of millions of years. As that magma ocean solidified, different minerals crystallized out at different times and sank or floated according to their density, with the last remaining pockets of liquid rich in exactly the kind of incompatible elements that don't fit neatly into normal crystal structures, potassium, rare earths, phosphorus, among them, becoming increasingly concentrated as the process went on. If that final, most enriched layer of liquid ended up preferentially trapped beneath one hemisphere rather than distributed evenly around the whole Moon, whether through some early asymmetry in cooling, or through the influence of Earth's gravity pulling more strongly on one side during the Moon's molten youth, it could help explain why the near side ended up so chemically different from the far side, long before a single volcano ever erupted. It is a reasonable, well-supported hypothesis. It is also, notably, not mutually exclusive with the idea Professor Tian's team would eventually propose. A Moon that started out with an unevenly distributed magma ocean, its most enriched material already concentrated toward one hemisphere, could still have had that asymmetry sharpened, or partially reinforced by a later, separate catastrophe. The ancient global unevenness and the specific localized potassium boiling detected in the Chang'e 6 basalts are not necessarily competing explanations. They may simply be two different chapters of the same long, layered story, one written in the moon's first 100 million years and the other burned in somewhat later, in a single violent afternoon in the southern hemisphere of the far side. There is another detail worth sitting with here, something that becomes clear only once you start comparing the timeline of the South Pole Aitken impact against the broader history of lunar volcanism. The basin itself formed extraordinarily early, somewhere between 4.2 and 4.3 billion years ago, in the first few 100 million years of the moon's existence, while the magma ocean was likely still finishing its slow crystallization, or had only just recently finished. The basalts that Chang'e 6 actually collected, the ones carrying the heavy potassium signature, are considerably younger, dated to somewhere between 2.79 and 2.87 billion years old. That means there is a gap of well over 1 billion years between the moment the basin was carved and the moment the lava that eventually cooled into the sampled rock actually erupted onto the surface. Why does that gap matter? Because it tells you the heavy potassium signature measured in those 4 fragments was not simply frozen into place the instant the ancient impact occurred, like a photograph capturing a single fleeting moment. It had to persist, quietly, for well over 1 billion years, sitting dormant in the deep mantle beneath the basin, waiting through unimaginable stretches of geological time before finally rising to the surface as fresh magma and cooling into solid rock that a robotic scoop 4.5 billion years later would eventually disturb. That is not a fleeting fingerprint. That is closer to a scar that never fully healed. A piece of chemical damage carried forward through more than 1/3 of the entire age of the solar system, preserved in the deep interior of a small, airless world with no plate tectonics to ever recycle it away, no ongoing volcanism to ever refresh or dilute it, nothing at all to erase it except the patient passage of time itself. And that, in many ways, is one of the quiet, underappreciated advantages the moon offers scientists that Earth simply cannot. Earth's own crust is constantly recycled, folded back down into the mantle through plate tectonics, melted, reformed, and erased over timescales of a few 100 million years at most. Almost nothing on Earth's surface is old enough to remember an event from 4.5 billion years ago directly. The moon, lacking plate tectonics entirely, lacking any real atmosphere to weather its surface, lacking flowing water to erode it, is in many ways a far better archive of the early solar system than our own planet ever could be. Whatever happened here billions of years ago is still, in a very real sense, lying on the surface, waiting for someone with the right instruments and the right patience to come and read it. Which is precisely what Chang'e 6 did. Not by discovering something entirely unknown to science in a philosophical sense, since planetary scientists had suspected for decades that a moon-scale impact might be capable of vaporizing volatile elements under the right conditions, but by finally providing the one thing every previous theory about the lunar dichotomy had been missing: actual physical proof, pulled directly from actual rock, collected from the one hemisphere of the moon that had never before given up a single gram of itself to human hands. Part 7. The other things hiding in the dust. Potassium and iron were not the only stories buried inside that small collection of far-side material. They were simply the story that made the loudest, cleanest headline, the one clear enough and dramatic enough to anchor an entire published paper around. But nearly 2 kilograms of soil. examined by dozens of separate research groups working in parallel, inevitably surrendered more than one secret. And some of the smaller findings, quieter and less immediately explainable, may end up mattering just as much in the long run. Take water, or, more precisely, take the near-total absence of it. One of the most closely watched questions in modern lunar science concerns how much water the moon's interior actually holds, locked away not as ice, but as hydroxyl molecules bound directly into the crystal structure of certain minerals, invisible to the naked eye and detectable only through careful laboratory analysis. This matters enormously for understanding how the moon formed in the first place. The leading theory of lunar origin holds that the moon coalesced from debris flung into orbit around Earth after a Mars-sized body, sometimes called Theia, struck the young Earth in a glancing collision billions of years ago. That kind of violent, high-energy formation should, by most models, have left the resulting moon extremely poor in volatile elements, including water, since so much material would have been vaporized and lost to space in the aftermath. For years, near-side samples complicated that picture. Small amounts of water, more than expected under a simple violent formation model, were detected locked inside volcanic glass beads and certain mineral grains brought back by the Apollo missions and later by Chang'e 5, suggesting the moon's interior was not quite as bone-dry as the classic giant impact theory predicted. It was one of the small, persistent anomalies that kept lunar formation theorists busy revising their models for years. The Chang'e 6 basalts, when tested for the same signature, came back drier, measurably, consistently drier than their near-side counterparts. Less structurally bound water locked into the mineral grains. Less overall evidence of a volatile, rich source region deep beneath the far-side crust. Combined with the potassium findings, a pattern begins to emerge that is hard to look away from. Wherever you look in this far-side sample, the volatile elements, the ones that evaporate easily under heat, the ones that make magma flow more readily and erupt more often, seem to be missing, or at least significantly reduced, compared to what has always been measured on the near side. Is that because the ancient South Pole Aitken impact boiled the local water away in the same violent afternoon that boiled away the potassium, through the exact same physical process, simple evaporation into an airless vacuum? Or is it because the far side mantle was always somewhat drier than the near side mantle, right from the earliest days of the moon's formation, for reasons that trace back to that uneven magma ocean we discussed a moment ago, entirely independent of any later impact? The honest answer at this stage in the research is that nobody can yet say for certain, and the scientists working directly with the samples have been careful not to claim more certainty than the data currently supports. It may, quite plausibly, be some combination of both explanations working together, an already somewhat depleted region of mantle that was then further stripped of its remaining volatiles by one catastrophic ancient collision. There is also the matter of age itself, and a puzzle it quietly reopened. Before Chang'e 6, the youngest confirmed lunar volcanic activity, based on samples actually collected and dated in a laboratory, came from Chang'e 5, whose basalts were dated to a surprisingly young 2 billion years old, far younger than most scientists had expected active volcanism to persist on such a small, rapidly cooling world. It had already forced a partial rewrite of how long the lunar interior could realistically stay hot enough to produce fresh lava. The Chang'e 6 basalts, dated to somewhere between 2.79 and 2.87 billion years old, sit comfortably in between the oldest Apollo basalts and the surprisingly young Chang'e 5 material, filling in a gap in the timeline that scientists had previously had to bridge with models and extrapolation rather than actual physical evidence. That might sound like a minor bookkeeping detail, but it genuinely is not. Every additional confirmed data point on the timeline of lunar volcanism tightens our understanding of exactly how the moon's interior cooled over billions of years, how long different regions of the mantle stayed hot enough to melt, and how uneven that cooling process actually was from one hemisphere to the other. Before Chang'e 6, every single confirmed sample on that timeline came from the near side or from the moon's more common near equatorial regions, having even a single confirmed data point from deep within the largest impact basin on the far side, a region with a documented unusually thick crust and, as it now appears, an unusually depleted potassium-poor mantle gives researchers an entirely new anchor point to calibrate their models against, one that had simply never existed before this mission returned. Then there is the question of the impactor itself, the original object that struck the moon and dug out South Pole Aitken in the first place, the true origin of which remains even now genuinely unresolved. We know its approximate age. We know, roughly, how much energy it must have carried and how deep its effects reached. What we do not know with any real confidence is exactly what kind of object it actually was. An asteroid, a comet, unlikely given the region's composition but not entirely ruled out. Some larger, more exotic body left over from the earliest, most chaotic phase of solar system formation, when planet-sized objects were still colliding and merging on comparatively short timescales. Professor Tian's team, in the course of ruling out possible contamination sources for the heavy potassium signature they measured, tested several candidate impactor compositions and found none of them cleanly matched what would be needed to explain the data. That is a genuinely interesting negative result in its own right. It suggests that whatever struck the moon at South Pole Aitken was not simply a common, well-understood type of asteroid, the kind whose chemical fingerprint scientists already have a firm handle on from studying meteorites that have fallen to Earth. It may have been something rarer, some rocky wanderer from an earlier, less well-documented population of solar system debris. One that either no longer exists in significant numbers today, or one whose surviving members simply have not yet been identified and studied by modern meteorite science. This is, in its own quiet way, one of the more tantalizing loose threads left dangling by the entire mission. Somewhere out there, or more likely, entirely consumed and gone, obliterated in the very collision that made it famous, was an object whose true identity we may never fully recover. All we have left of it is the wound it left behind, 4.5 billion years old, still readable today in the isotopic ratios of a handful of milligram-sized basalt fragments. And then there is the broader, almost philosophical question that has quietly hung over every part of this mission from the very beginning. If a single impact, striking a moon that was still young and only partially cooled, was capable of reaching down into the mantle and boiling away measurable quantities of volatile elements, what does that tell us about impacts in general, on other worlds, in other times? The early solar system was, by every reconstruction scientists have managed to piece together, an extraordinarily violent place. Planet-sized collisions were not rare, isolated events confined only to the moon. Mercury, Mars, Earth itself all bear evidence of catastrophic ancient bombardment, evidence that in many cases has been erased, buried or eroded away over billions of years of subsequent geological activity, atmosphere, and, on Earth at least, flowing water, and shifting continents. The moon, precisely because it lacks all of that erasing machinery, may be quietly preserving a far more accurate, far more legible record of exactly how violent and exactly how chemically transformative those ancient impacts actually were, not just for our own small corner of the solar system, but potentially as a general principle applicable to rocky worlds everywhere. If the physics revealed by these 4 small fragments holds true more broadly, then giant ancient impacts may have played a far larger role in shaping the chemical identity of planetary interiors, not just their surface geography, than scientists have generally given them credit for. Every rocky world with a violent early history, every moon, every planet that formed amid the same chaotic bombardment that once tore across our own solar system, may carry hidden inside it the same kind of quiet, isotopic scar tissue that Chang'e 6 just found on the far side of our own moon, waiting, in each case, for someone to go and physically pick up a handful of the right rock. Part 8. What it took to reach the far side at all. It is worth stepping back for a moment from the chemistry and the isotopes and sitting instead with the sheer engineering audacity of what actually had to happen for any of this to be possible in the first place. Because landing on the far side of the moon is not simply landing on the moon with a slightly worse view of Earth. It is, in almost every meaningful sense, an entirely different technical problem, one that had never been solved by any nation on Earth before China accomplished it, first with an earlier mission in 2019, and then again, this time with a full sample return, in 2024. Every crewed and robotic mission that had ever successfully landed on the moon before that, every Apollo landing, every Soviet lunar probe, every earlier Chinese Chang'e mission had touched down on the near side or close enough to the edge of it that direct radio contact with Earth remained possible throughout the entire descent and surface operation. Mission control could watch telemetry arriving close to real time. If something went wrong during descent, there was, at least in principle, a narrow window in which a human being on the ground could intervene, issue a correction, abort a maneuver, make a judgment call. None of that was available on the far side. The moment a spacecraft descending toward the Apollo basin dropped below the lunar horizon as seen from the relay satellite's vantage point, or the moment any signal simply had to travel through more than 3,000 kilometers of solid rock to reach Earth directly, human intervention became physically impossible, not because of policy or caution, but because of the basic geometry of the situation. Radio waves travel in straight lines. The moon itself was standing directly in the way. This is why the entire 17-minute descent sequence, from an altitude of 200 kilometers down to a soft touchdown on the crater floor, had to be handled entirely by the spacecraft's own onboard systems, with no possibility of a human correcting course partway through. The lander's autonomous system had to identify hazards, boulders, steep slopes, shadowed depressions that might conceal a drop-off, using its own cameras and laser scanner, and then had to make its own decisions about where exactly to touch down, adjusting its trajectory in real time entirely on its own judgment. Engineered years in advance by teams of programmers who had to anticipate every plausible scenario the spacecraft might encounter without ever being able to watch it happen live and step in. The relay satellite, Queqiao, deserves particular attention here because without it, none of the rest of the mission architecture would have been possible at all. It sits at what is known as the Earth-Moon L2 Lagrange point, a specific location in space, roughly 65,000 kilometers beyond the far side of the moon, where the combined gravitational pull of the Earth and Moon, along with the satellite's own orbital motion, allows it to maintain a stable position relative to both bodies without requiring constant fuel expenditure to hold its place. From that vantage point, it can see both the far side of the Moon and the Earth simultaneously at all times, acting as a permanent bridge between the two. Every single command sent to Chang'e 6 during its time on the far side, every scoop of soil, every drill sequence, every image beamed back showing the lander sitting alone on that ancient basalt plain, had to travel first from Earth up to Qichao, and then from Qichao down to the spacecraft on the surface, and the return journey had to happen in reverse. It is, in the most literal sense, a relationship built on a single point of failure, 65,000 kilometers past the near edge of human reach, quietly holding open a channel of communication that the entire mission depended on completely. The choice of landing site itself, deep inside the Apollo basin, nested within the far larger South Pole Aitken Basin, added its own layer of difficulty on top of all this. Basins of this age and scale tend to have genuinely rugged, complicated terrain, wrinkle ridges, scattered kipukas of older exposed rock, small secondary craters left behind by later, smaller impacts scattered across the plain. Choosing a landing ellipse precise enough to guarantee a safe touchdown, while still sitting close enough to the deepest, most scientifically promising material the basin had to offer, required years of careful analysis of high-resolution orbital imagery gathered by earlier reconnaissance missions specifically to scout potential landing zones long before Chang'e 6 ever launched. And then, once safely down, the sampling itself had to be conducted with a level of precision that left almost no room for error because there would be no second attempt. Unlike a rover mission, which might spend months or years slowly exploring a landing site and gradually building up a picture of its surroundings, Chang'e 6's entire surface operation, from touchdown to the ascent vehicle's liftoff, had to be completed inside a window measured in mere hours, dictated by the need to synchronize the moment of ascent with the orbital position of the waiting service module overhead, ready to receive the sample container. There was no leisure in any part of this. Every single step, the scooping, the drilling, the rover's brief excursion to photograph the lander, all of it had to happen within a tightly compressed timeline that had been planned down to the minute, years in advance, executed autonomously on a hemisphere of the Moon where no human being had ever set foot, watched over from Earth only through the narrow, precious channel of a single relay satellite parked in the dark between two worlds. When you consider all of that together, the achievement being celebrated at that formal ceremony in Beijing was never really just about the soil itself, remarkable as the soil turned out to be. It was about proving, for the first time in the history of spaceflight, that a nation could reach around to the hidden hemisphere of our nearest neighbour, operate there entirely without direct human oversight during the most critical minutes of the mission, and bring a piece of it home safely, intact, across a 53-day journey spanning launch, lunar orbit insertion, an autonomous landing, sample collection, an autonomous liftoff, an autonomous docking maneuver in lunar orbit, a trans-Earth journey, and finally a skip re-entry through Earth's atmosphere, ending in a parachute descent onto the grasslands of Inner Mongolia. Every one of those steps had a predecessor somewhere in the history of spaceflight. Robotic sample returns from the Moon had been accomplished before by both the American and Soviet programs decades earlier, and by China itself with Chang'e 5 in 2020. Autonomous lunar landings had been accomplished before. Lunar orbit rendezvous and docking had been accomplished before. First by the crewed Apollo program, and later robotically. What had never been accomplished before, not once, by anyone, was stitching every single one of those individual technical achievements together into a single unbroken chain, with the added and entirely unprecedented complication of doing it all on a hemisphere of the moon that had never once, in the history of spaceflight, been in direct radio contact with the Earth. That is the quiet, easily overlooked engineering achievement sitting underneath all the geochemistry we have spent tonight walking through. Before there could be any conversation about heavy potassium isotopes or vaporized mantle material or the ancient scar tissue of a 4.5 billion year old impact, there first had to be a spacecraft capable of getting there, working entirely alone on the far side of a world with no one watching in real time, and getting back. Part 9. The dichotomy problem revisited. Let's return now to the larger question this entire mission was built to help answer, because it is worth laying it out again with everything we now know, rather than everything we merely suspected before Chang'e 6 flew. The lunar dichotomy, the stark difference between the dark, volcanic near side and the pale, heavily cratered far side, has been recognized as a genuine scientific puzzle since the very first spacecraft images of the far side came back in 1959. And over more than 60 years of study, 3 broad families of explanation have competed for dominance, sometimes complementing each other, sometimes standing in direct tension. The first family centers on the ancient magma ocean, the ideas we touched on earlier, that the young moon, shortly after its formation, was covered by an enormous deep sea of molten rock that slowly crystallized over tens of millions of years, and that some early asymmetry in how that ocean cooled, whether from Earth's tidal heating warming one hemisphere more than the other, or from some other subtle imbalance in the moon's earliest structure, left the near side enriched in the kind of heat-producing, volcanically favourable material that would go on to fuel billions of years of eruptions, while the far side ended up comparatively depleted from the very start. The second family centres on impacts, the idea that one or more large collisions striking the moon at different points in its early history physically reshaped its interior structure in ways that had lasting consequences for volcanic activity. This is the family of explanation that Chang'e 6's potassium findings speak to most directly, suggesting that the South Pole Aitken impact specifically may have stripped volatile elements from the local mantle through simple, brutal vaporization, making that region measurably less capable of producing magma for billions of years afterward. The third family, less discussed but still seriously considered, involves the moon's thermal evolution more broadly, the idea that Earth's own gravity, tugging asymmetrically on the young moon as it slowly settled into its current tidally locked configuration, may have influenced internal heat flow and crustal thickness in ways that favoured volcanism on the Earth, facing hemisphere over billions of years, independent of any single dramatic event, through slow, patient, ongoing gravitational influence rather than sudden catastrophe. What makes the Chang'e 6 findings genuinely significant rather than simply interesting is that, for the first time, one of these competing explanations has actual physical, laboratory-verified evidence behind it, drawn directly from material collected at exactly the location the theory predicted should show its effects most clearly. That is a meaningfully different scientific position to be in than having 3 plausible but untested hypotheses floating in competition with each other, each supported only by orbital remote sensing and computer modelling. But it would be a mistake, and the researchers themselves have been careful to avoid this mistake, to conclude that the impact hypothesis has now single-handedly won the argument that the mystery of the lunar dichotomy has been definitively solved. Real science rarely resolves itself so cleanly. It is entirely possible, and in fact seems increasingly likely given everything the samples have revealed, that all three families of explanation are true simultaneously, each one contributing a portion of the final picture layered on top of one another across billions of years of lunar history. Picture it this way. The young moon, shortly after formation, cools from its molten magma ocean state with some early degree of hemispheric imbalance already built in, whether from Earth's gravitational influence or from the simple, chaotic randomness of how a global ocean of molten rock happens to crystallize. That imbalance leaves the near side already somewhat more enriched in heat-producing elements than the far side, a head start of sorts, in the long competition for volcanic activity that would play out over the following billions of years. Then, in the earliest few 100 million years of lunar history, while the interior is still hot and only partially settled, an enormous impact strikes the far side, carving out what would become the South Pole Aitken Basin, and, in doing so, briefly heats the local mantle hot enough to boil away a portion of its remaining volatile elements, further widening the gap between the two hemispheres, reinforcing an asymmetry that already existed rather than creating it from nothing. And then, over the following 4 billion years, that reinforced imbalance simply compounds on itself. The near side, already warmer, already richer in the elements that make magma easier to produce, continues erupting lava for far longer than the far side does, eventually building up the broad, dark seas that give the moon its familiar face, while the far side, already cooler and already depleted, produces only scattered, comparatively modest volcanic activity, visible today as small, isolated patches rather than vast connected plains. If something like that combined picture turns out to be correct, then the lunar dichotomy stops looking like a single unsolved mystery with one correct answer waiting to be found, and starts looking instead like a layered historical record, not unlike the way a geologist reads the walls of a canyon on Earth, each stratum telling a chapter of a much longer story, no single layer sufficient to explain the whole formation on its own. This is, in many ways, a more satisfying answer than any single dramatic explanation could have been, even if it is a messier one to summarize in a single sentence. It means the moon's two faces are not the result of one clean, isolated event, but the accumulated consequence of billions of years of overlapping processes, gravitational, thermal and violent, each leaving its own mark, some of them reinforcing each other, some of them possibly working in tension, all of them eventually adding up to the two starkly different hemispheres we see today whenever we look up, and whenever, for the very first time in human history, we finally manage to look behind. There is a broader lesson buried in this too, one that reaches beyond the moon entirely. For decades, planetary scientists studying rocky worlds across the solar system have debated how much weight to give impacts versus internal processes when trying to explain large-scale asymmetries and surface features. Mars has its own version of this exact puzzle, a dichotomy nearly as dramatic as the moon's, with smooth northern lowlands standing in stark contrast to heavily cratered southern highlands. A divide that planetary scientists have spent decades arguing over, torn between impact-based explanations and internal, mantle-driven ones. In an argument that echoes almost exactly the one we have just walked through regarding our own moon. The methodology Chang'e 6 demonstrated, actually landing in the specific region a competing hypothesis predicted should show physical evidence, and then testing that hypothesis directly against real returned material rather than remote sensing data alone, offers something valuable well beyond the specific answer it produced about our own moon. It offers a template, a demonstration that these kinds of deep, ancient planetary mysteries, the ones that have sat unresolved through decades of orbital observation and computer modeling alone, may ultimately require exactly this kind of direct, physical, sample-based confrontation to move meaningfully closer to resolution. Sometimes, no matter how sophisticated the remote instruments become, no matter how detailed the gravity maps or the mineral spectra grow, there really is no substitute for simply going, landing, and bringing a piece of the actual ground back home to a laboratory bench. Part 10. What still doesn't add up. For all that Chang'e 6 managed to reveal, it would be dishonest to leave you with the impression that the mission tied everything up neatly, that the mystery of the lunar far side has now been closed and filed away. Real science almost never works that cleanly, and this case is no exception. Sitting alongside every genuine discovery the mission produced are a handful of loose threads, results that do not quite fit the tidy story we have been building tonight, and that the scientists working directly with the samples have been careful and honest about flagging rather than smoothing over. The first of these concerns scale. 4 fragments. That is the entire physical basis, so far, for the heavy potassium signature that anchors the impact boiling hypothesis. 4 small stones, the heaviest of them weighing barely as much as a single grain of rice, pulled from a return sample containing nearly 2 kilograms of material. It is an entirely defensible sample size for the kind of ultra-precise isotope work the team was conducting. Work that genuinely does require painstakingly small, carefully selected fragments rather than bulk material. But it also means the finding, striking as it is, currently rests on a foundation narrow enough that a single unusual fragment, an outlier for reasons not yet understood, could meaningfully shift the picture once a larger set of samples is eventually analyzed. The team knows this. It is precisely why their published conclusions are worded so carefully, framed as evidence the impact contributed to the dichotomy, not as proof that it single-handedly explains it. The second loose thread concerns the timing gap we touched on earlier, the more than 1 billion years separating the original South Pole Aitken impact from the actual formation of the basalts Chang'e 6 collected. That gap is not in itself a problem for the impact hypothesis. It is entirely plausible, even expected, for a heat-altered region of mantle to sit dormant for a long stretch of geological time before eventually producing fresh magma. But it does mean that the direct causal chain, impact heats, mantle boils off potassium, that same mantle later melts and rises as lava, cannot be observed directly. It has to be inferred carefully through modelling and elimination of alternative explanations, rather than watched unfold step by step in the geological record the way you might trace a more recent, better documented process. Every one of the team's controls, ruling out cosmic ray exposure, ruling out surface contamination, ruling out ordinary magmatic fractionation, ruling out various impactor compositions, exists precisely because that direct chain of causation cannot simply be observed. It has to be argued for rigorously against every plausible alternative anyone can think of. There is also the question of how representative the Chang'e 6 landing site actually is of the South Pole Aitken Basin as a whole. The basin itself spans roughly 2,500 kilometers, an area larger than many countries on Earth. Chang'e 6 sampled a single point within it, on the floor of the smaller Apollo basin nested inside the larger structure. It is entirely possible, even likely, that different regions of South Pole Aitken experience different degrees of heating, different depths of excavation, different mixtures of local and foreign material, depending on their specific position relative to the original point of impact. The heavy potassium signature measured at this one location may not be uniform across the entire basin. It may be a localized effect, strongest near whatever the exact center of the original impact turns out to have been, and weaker or entirely absent in basalts that might one day be collected from other parts of the same basin. This is precisely why the research team has been explicit about wanting to extend their analysis to other volatile elements beyond potassium and iron, and why future missions to other locations within South Pole Aitken carry so much scientific weight. A single data point, however carefully measured, is a hypothesis with strong supporting evidence. A pattern confirmed across multiple independently sampled locations within the same basin would be something considerably closer to an established fact. There is a further complication, one that has less to do with the samples themselves and more to do with the broader theoretical framework surrounding them. The idea that a large impact can vaporize a meaningful fraction of a planetary mantle's volatile content is not, strictly speaking, a brand new concept invented for this study. Planetary scientists have long modeled similar processes in the context of Earth's own formation and in the formation of the Moon itself, since the leading theory of lunar origin already requires substantial vaporization of material during the original giant impact that is thought to have created the Earth-Moon system in the first place. What Chang'e 6 provided was not a new theoretical mechanism, but the first direct physical confirmation that this kind of process can also occur locally within an already formed planetary body as the result of a later, smaller scale impact rather than the original formation event itself. That distinction matters because it opens a genuinely new line of scientific questioning that extends well beyond the Moon. If a single large impact striking an already formed, already cooled planetary body can meaningfully alter the volatile chemistry of its interior, then every rocky world in the solar system with a documented history of large impacts, and that includes essentially all of them, may carry similar hidden chemical scars waiting to be found in exactly the way this one was found, by landing in precisely the right place and asking precisely the right question of a small enough handful of rock. Mercury, battered relentlessly by impacts throughout its history and possessing a surface that, much like the Moon's far side, seems unusually depleted in certain volatile elements relative to what simple formation models predict, is an obvious candidate for this kind of thinking. Mars, with its own ancient impact-scarred southern highlands, is another. Even asteroids and smaller planetary bodies, less studied and less understood than the Moon, but increasingly accessible thanks to a new generation of robotic sample return missions launched by multiple space agencies over the past decade, may carry their own versions of this exact story, waiting in laboratories for someone to notice. None of this is settled. All of it is, in the truest and most exciting sense of the phrase, still an open question, sitting exactly where good science tends to sit, at the narrow, uncomfortable edge between a compelling new idea and a fully confirmed fact, waiting on more data, more samples, more missions, more careful, patient work in laboratories on Earth to eventually settle which parts of the picture are correct, which parts need revision, and which parts nobody has even thought to ask about yet. What can be said with real confidence, though, is this. Before Chang'e 6, the lunar dichotomy was a puzzle argued almost entirely from a distance, through orbital gravity maps, spectral surveys, and computer models built on assumptions that could never quite be tested directly. After Chang'e 6, for the first time in more than 60 years of studying this question, there is actual rock on a laboratory bench, collected from exactly the region every competing theory had long pointed to as the most important place on the entire moon to look. And that rock is finally starting to talk. Part 11. What comes next? The story of Chang'e 6 does not end with a single published paper in January, and it was never going to. Nearly 2 kilograms of far-side material now exist on Earth, and the overwhelming majority of it, by mass, has not yet been touched by any instrument. What has happened so far? The density measurements, the mineral catalogue, the potassium and iron isotope work, represents the earliest, most urgent wave of analysis, the kind of work that gets done quickly, precisely because it answers foundational questions everything else depends on. What comes next is slower, quieter, and in some ways more consequential. China has begun distributing small allocations of the returned material to research institutions across the country, following a formal application process not unlike the one that has governed access to Apollo samples for the past half-century. Scientists submit detailed proposals explaining exactly what they intend to measure, why it matters, and how much material they would need. And a review process determines who receives an allocation and how much. This is standard practice in lunar science, born of hard experience. Every gram of returned material is irreplaceable, effectively impossible to recollect, and every measurement that consumes or alters a sample forecloses some other future measurement that might have been made instead. Allocations tend to be granted cautiously, in small quantities, with strong preference given to techniques that preserve as much of the original material as possible for future researchers working with instruments and methods that do not yet exist. The China National Space Administration has stated publicly that it welcomes proposals from international researchers as well, extending an invitation that mirrors, in spirit, if not in exact procedure, the way Apollo samples have been shared with scientists outside the United States for decades. Whether that international collaboration unfolds smoothly and how quickly remains to be seen. Scientific collaboration across national space programs has often moved at the pace of diplomacy as much as the pace of curiosity, and lunar sample sharing in particular has a long, occasionally complicated history behind it. But the stated intention at least is there, an open door rather than a closed one. Meanwhile, the broader scientific community has already begun the work of placing the Chang'e 6 findings into a larger context, running new models, revisiting old datasets from orbital missions with these fresh ground truth measurements in hand. The catalogue of 1,674 candidate source craters we mentioned earlier is itself a snapshot of exactly this kind of work, researchers working backward from the physical evidence in the sample container to reconstruct, crater by crater, exactly which ancient impacts across the far side contributed material to that one patch of ground inside the Apollo basin. That kind of detective work will likely continue for years, refined as better orbital imagery becomes available and as more researchers bring their own specialized expertise to bear on the puzzle. There is also the matter of the missions still to come. The South Pole Aitken Basin has become, almost overnight, one of the single most scientifically prioritized targets in the solar system, not just for China, but for multiple space agencies pursuing their own independent lunar programs. Part of that interest predates Chang'e 6 entirely, driven by the long-standing hope of finding water ice preserved in permanently shadowed craters near the lunar South Pole, craters where sunlight has genuinely never once reached the floor across billions of years. Cold enough to have trapped and preserved ice for the entire history of the solar system. But the Chang'e 6 findings have added an entirely new dimension to that interest, because the basin is no longer simply a promising place to look for water ice on the surface. It is now a confirmed, physically verified window into the deep mantle of the moon. A place where a single ancient act of violence appears to have reached down and rearranged the fundamental chemistry of an entire hemisphere. Future missions, whether robotic or eventually crewed, that manage to sample different locations within South Pole Aitken, closer to what may have been the true center of the original impact, or further from it at different depths. In different types of terrain, we'll be able to directly test whether the potassium signature Chang'e 6 found is a localized quirk specific to the Apollo basin, or whether it extends more broadly across the entire South Pole Aitken structure. That single question, seemingly narrow, actually carries enormous weight, because the answer will determine just how large a role this one ancient impact really played in shaping the volcanic history of an entire hemisphere of the moon. There is also a slower, quieter kind of significance to all of this, one that has less to do with any single measurement and more to do with what the mission demonstrated was possible. For 60 years, the far side of the moon sat as a kind of scientific frontier defined almost entirely by absence, a hemisphere we could photograph but not touch, model but not verify, theorize about but never directly confront with physical evidence. Chang'e 6 closed that gap, not completely, not permanently, but for the first time, meaningfully. It proved that a spacecraft could descend, operate, collect, and return from that hidden hemisphere with no direct line of communication to Earth during the most critical phase of the mission. Relying entirely on a relay satellite parked in the dark and on autonomous systems trusted to make their own decisions in real time, 400,000 kilometers from the nearest human being. Every mission that follows, whether from China or from any other space program pursuing its own ambitions in this same region, inherits that proof of concept. The far side is no longer untouchable in the way it was for the first 60 years of the space age. It is difficult, still demanding, still requiring the kind of relay infrastructure and autonomous precision that took decades to develop. But it is no longer impossible, and that distinction matters enormously for how quickly this particular scientific frontier is likely to open up over the coming years. There is one more thread worth mentioning before we begin to close out tonight's story, one that reaches slightly beyond the pure science and into something a little more human. The character-shaped hole left behind by the drill, the one that spread across social media within days of the sample return. Unplanned, unintentional, simply the shape a narrow drill happens to leave in soft lunar soil when it is withdrawn straight back out. It is a small, almost throwaway detail in the grand scope of everything this mission accomplished. But it captures something real about how these moments land in the public imagination as much as in a scientific journal. A robotic arm operating entirely on its own 400,000 kilometers from home on a hemisphere of the moon no human eye had ever directly seen, happened to leave behind a mark that looked, to anyone glancing at the photograph, uncannily deliberate. Nobody designed it. Nobody could have designed it. And yet there it was, a small accidental signature at the bottom of the largest impact basin in the solar system, on the same patch of ground that would go on to yield the first direct evidence that an ancient collision once boiled part of the moon. Part 12. The face we finally reached. So where does that leave us, sitting here at the end of a story that began with a simple, almost naive question. Why does the moon look the way it does? We have walked through billions of years tonight, a young moon, freshly formed, still glowing with the heat of its own creation, covered edge to edge in a global ocean of molten rock, slowly crystallizing into the crust we know today. A colossal impact, striking somewhere in the first few 100 million years of that young moon's life, carving a wound 2,500 kilometers wide into its southern far side, a wound so deep it may have reached straight through the crust and into the mantle itself. A burst of heat, brief in cosmic terms but ferocious enough to have briefly pushed the local mantle to temperatures approaching 3,000 Kelvin, hot enough to boil solid rock, hot enough to drive potassium and iron straight out of the mineral structures that had held them since before the moon existed at all, sending the lighter isotopes drifting off into the vacuum of space and leaving the heavier ones behind, quietly, patiently, waiting, and then silence over 1 billion years of it. The scarred mantle beneath that basin sitting dormant, its chemistry permanently altered, while elsewhere on the moon, on the hemisphere facing Earth, lava continued to rise and flood and cool, again and again, building up the broad dark plains that would one day give the near side its familiar, comforting face. Until finally, somewhere around 2.8 billion years ago, that same scarred, depleted mantle beneath South Pole Aitken produced one last pulse of magma of its own, rising up through the crust, flooding the floor of a smaller crater nested inside the larger basin, and cooling there into solid basalt, carrying its billion-year-old secret frozen inside its mineral structure, waiting through the entire remaining history of the moon, waiting while Earth's own oceans filled and its continents drifted and its first simple life took hold, waiting through the entire span of human history, every civilization that ever rose and fell while looking up at the same familiar, one-sided moon, never once suspecting that its other face told a completely different story. Waiting through the first grainy Soviet photograph in 1959 that finally showed us what that other face even looked like. Waiting through 6 Apollo landings and 3 earlier robotic sample returns, every one of them reaching only the near side, every one of them building a picture of the moon that was, however carefully constructed, quietly incomplete. And then, in the spring of 2024, a spacecraft descended entirely on its own judgment, 400,000 kilometers from the nearest human being, guided only by its own cameras and its own laser scanner and its own onboard reasoning, and settled gently onto the floor of that same small crater. A scoop reached out, a drill bit down, and a piece of that billion-year-old secret was finally lifted free of the ground that had held it since before there were eyes on Earth capable of looking up and wondering what it meant. 53 days later, it was sitting in a laboratory in Beijing, and within months, 4 fragments of it, each one barely the weight of a raindrop, were dissolved, purified, and fed into a machine sensitive enough to read a difference in isotope ratios smaller than 2 parts in 10,000. And that machine told a story nobody had been able to prove before, that the dark seas we have looked up at our entire lives, the ones every culture on Earth found their own meaning in, a face, a rabbit, a woman with a water jar, are not simply a feature of the moon. They are the surviving half of a story whose other half was quietly erased billions of years ago in a single catastrophic morning that boiled part of a world and left the rest of it dark and heavy with memory of what it lost. We spend so much of our lives assuming that what we can see is the whole picture, that the face turned toward us is the only face there is. It took 60 years of spaceflight and one small, patient, autonomous machine willing to work entirely alone in the dark to prove that the moon, the same moon that has hung over every night of your life, has been keeping half of its history turned quietly away from us the entire time, not hidden by choice, not hidden by design, simply hidden by the slow, ancient mechanics of gravity, locking one face forever toward home and one face forever away. And now, for the first time, a small handful of that other face is sitting on a shelf in a laboratory on Earth, waiting for the next question, and the one after that, and the one after that. Somewhere in that container, mixed into the dust and the glass and the welded fragments of ancient breccia, there may still be grains nobody has looked at yet, carrying stories nobody has read yet, about a world that has always had two faces, and that only now, so quietly, so recently, has finally let us see what the other one has to say. So the next time you look up and find that same familiar face hanging there, pale and patient above the rooftops, remember what's turned away from you in that exact same moment. A hemisphere still cooling from a wound half as old as the solar system itself. 1 billion years of silence held inside a handful of dust, waiting patiently in a drawer in Beijing for someone to ask it the right question. The moon has been keeping half of itself hidden since before there was anyone here to notice, not out of secrecy, just the quiet, patient mechanics of gravity, doing what gravity always does. And somewhere in that dust, there are still grains nobody has looked at yet. If tonight's journey to the far side helped carry you towards sleep, let it keep doing that work for someone else too. Leave the video playing, subscribe if you'd like more of these quiet nights among the stars, and tell me in the comments where in the world you drifted off from tonight. Sleep well.